Hello future pilots, let's start the second chapter of instrumentation, which is the airspeed indicator. So first I'm going to explain you the principle of operation. So in this image you can see that the aircraft is stationary and it is in still air. Still air means that there's no moving air, and that means that the aircraft is subjected to only static pressure and there's no dynamic pressure. But when the aircraft starts moving, the aircraft is subjected to a additional pressure, which is the dynamic pressure. Along with it, the static pressure also exists. So what is the total pressure? The total pressure aircraft is subjected to is the static pressure plus dynamic pressure. So let's read this one. The dynamic pressure experienced by the aircraft will vary with the speed of the aircraft through the air. So what this statement is saying that when the speed of the aircraft changes, the dynamic pressure changes. So it is very obvious, when the speed is increased, more air molecules hit the leading edges of the aircraft and thus the dynamic pressure increases. When the speed of the aircraft is reduced, less air molecules hit the leading edges of the aircraft and thus the dynamic pressure decreases. So here you can see a formula of dynamic pressure, which is dynamic pressure equals to half rho v square. Rho is the density of the air and v square is the true airspeed. So I'm going to explain you how dynamic pressure is dependent on the density of the air. So if we increase the density of the air, means that more air molecules hits the leading edges of the aircraft and thus more pressure is exerted on the leading edges and thus increasing the dynamic pressure. So if we calculate the dynamic pressure, we can actually indicate the airspeed. But we know that dynamic pressure does not exist on its own. It always exists with static pressure. So the function of the airspeed indicator is to isolate the dynamic pressure from the total pressure or the pitot pressure to indicate the airspeed. So next we're gonna study about the construction of the airspeed indicator, which is very important. So now we know that if dynamic pressure can be isolated from pitot pressure, it will indicate airspeed. So the function of the airspeed indicator is to isolate the dynamic pressure from pitot pressure and to display the dynamic pressure calibrated as airspeed. So I will explain you now how the airspeed indicator works. So we will look at two things. One is the instrument case and the another one is capsule. So in the capsule, pitot pressure is fed, meaning dynamic pressure plus static pressure is fed. So when the pitot pressure is fed, the capsule expands, and when the pitot pressure is reduced, the capsule contracts. And in the instrument case, static pressure is fed. So let's read this one. As both the static pressure inside the capsule and case are equal, any expansion or contraction of the capsule will be due to the dynamic pressure only, as the static pressure cancels each other out. So what this statement is saying is that the reason behind static pressure being fed into the instrument case is to cancel the static pressure of the inside the capsule, because as we know, to calibrate to indicate the airspeed, we just need to isolate the dynamic pressure from pitot pressure, and this is the reason static pressure of both the instrument case and the capsule cancels each other out, and only the contraction and the expansion is due to the dynamic pressure only, and thus indicating the airspeed. So when the dynamic pressure increases, the capsule expands and the needle rotates clockwise, indicating an increase in airspeed. And when the dynamic pressure is reduced, the capsule contracts and the needle rotates anti-clockwise, indicating a decrease in airspeed. And this is how an airspeed indicator works. So from the formula of dynamic pressure, which is dynamic pressure equals to half rho v square, we can understand that dynamic pressure does not only depends on the airspeed of the aircraft but also on the density of the air. So let's read this one. Dynamic pressure depends not only on the speed of the aircraft but also on the air density. The density varies with temperature and pressure and therefore with altitude. If the air is less dense, the airspeed required to produce the same dynamic pressure will have to be greater. So let me explain you. So as the altitude increases, we know that the density decreases, meaning that as we go up, the number of air molecules also decreases. And we know from the definition of dynamic pressure that the number of air molecules hitting the leading edges of the aircraft is what we call, and the pressure exerted on the leading edges of the aircraft by the air molecules is what is dynamic pressure. So to maintain the same dynamic pressure, the airspeed of the aircraft has to be increased because the density is decreased. So we have to, in exchange, we have to increase the airspeed to maintain the same dynamic pressure. So in short, we can say as aircraft's altitude increases, to maintain the same dynamic pressure, we have to increase the true airspeed of the aircraft. Remember, the ASI is actually sensing the dynamic pressure, which is represented on the dial of the ASI as airspeed. Therefore, the ASI can only indicate the true airspeed, that the density for which the instrument is calibrated. So what this statement is saying is that the needle of the ASI, we already know that the dynamic pressure is actually indicating the airspeed, and thus the needle is showing the dynamic pressure, right? So the dynamic pressure is equal to the true airspeed of the aircraft only at the density for which the ASI or the airspeed indicator is calibrated to. No allowance is made in the calibration for the change in density which occurs with change of altitude. So this is an error, right? Because as we know that the aircraft increases, this altitude increases, the density decreases, but the aircraft's dynamic pressure is only equal to the true airspeed of the aircraft at which the aircraft's density is calibrated to. So this is an error, and this error is called the density error. So now I will explain you the errors of airspeed indicator. The first error is that instrument error, which is the errors or the defects caused by the manufacturer or the manufacturing imperfections. Next error is position error, causes due to suction or turbulent airflow in the vicinity of pitot or static heads. I have already explained you in the previous video, but still I can give you a summary of it, that it happens due to suction effect around the vicinity of pitot and static heads, which causes to sense less static pressure. Next is the density error, inaccuracy caused because the instrument is calibrated to a specific air density, typically sea level at standard atmospheric condition, but does not adjust for changes in air density due to altitude and temperature during flight. So I have already explained you in the above. In the calibration only I have explained you this error, right? Next is the compressibility error. At low speeds, an airplane's movement doesn't squeeze the air in front of it, so the air just flows smoothly around the wings. But when flying faster than about 300 knots, the airplane pushes into the air so quickly that air molecules piles up and get squeezed or compressed in front of the plane. This is called compressible flow. The faster the plane goes, the more noticeable this becomes. It can even cause shock waves at very high speed. So what is compressibility error is that when the aircrafts are at slow speed, like the airspeed below 300 knots, so the air molecules in front of it doesn't pile up or get squeezed or get compressed. But when the aircraft's airspeed is more than 300 knots, the air molecules in front of the aircraft get squeezed or compressed. And this is what we call as compressed flow. And it may also cause shock waves at very high speeds. Alright. So there are 4 airspeeds. First is indicated airspeed. So when the indicated airspeed is corrected for instrument and position error, it becomes calibrated airspeed or rectified airspeed. When calibrated airspeed or rectified airspeed is corrected for compressibility error, it becomes equivalent airspeed. When equivalent airspeed is corrected for density error, it becomes true airspeed. So I have a trick to learn this, which is DCP. Let me write this. T for true airspeed, E for equivalent airspeed, R for rectified airspeed, I for indicated airspeed, D for density error, C for compressibility error, and P is for position or instrument error. So by this you can easily answer when there is a question. So indicated airspeed is corrected for position error to become rectified airspeed or calibrated airspeed. Calibrated airspeed is corrected for compressibility error to become equivalent airspeed, and equivalent airspeed is corrected for density error to become true airspeed. So next we're gonna study about airspeed color coding. So there are direct questions that what is the upper range and lower range of white arc, green arc or yellow arc, or what is the red radial line or blue radial line. So let's understand this, and you have to learn this. So the first arc is the white arc, denotes the flap operating range. So the upper range is VSO and the lower is VFE. What is VSO? VSO, the stall speed or the minimum steady flight speed in the landing configuration. Right, it is the stall speed in the landing configuration. And the lower range states VFE, which is the maximum flap extension speed. So it is the maximum speed at which the flaps can be extended. Next one is the green arc, denotes the normal operating speed range. Alright. So the upper says VS1 and the lower is VNO. What is VS1? VS1, the stall speed or the minimum steady flight speed in a specified configuration. Alright, the stall speed in a specified configuration. And the lower one, which is the lower range, states VNO. It is the normal operating speed. The maximum normal operating limit speed. Alright. The next one is the yellow arc. Upper one states VNO and the lower one is VNE. VNO already we know the maximum normal operating limit speed. And the lower one states VNE, which is the never exceed speed. We cannot exceed this speed because it will cause damage to the aircraft. Next is the red radial line. It also denotes the VNE, the never exceed speed. Next is a blue radial line. So what does this blue radial line denotes is that the best rate of climb speed for one engine out, maximum weight at mean sea level, which is also we call VYSE. Alright, it is here. So it is the speed at which if an engine goes out, it will give us the best rate of climb. Alright. So next we're gonna study pitot and static blockages. This is very important for your examinations because most of the questions are like, if pitot is blocked, then what happens to the ASI, or static is blocked, what happens to the ASI, right? So the first situation is that when the pitot head becomes blocked but the aircraft is on the same altitude. So what happens is that the capsule, we know that the contraction and the expansion of the capsule is due to the dynamic pressure only. And as the static pressure inside the instrument case and the capsule is same, it cancels each other out. But as the pitot head is blocked, that means that if the pitot head is blocked, then there is no change in dynamic pressure, and thus there is no change in the indication, and thus the needle remains in the same position. So in the conclusion, what it is written is that if the pitot head becomes blocked, the ASI reading will in general remain unchanged. Alright. Next situation is that when there is a change in altitude with pitot head block. Okay, there's a change in altitude. Okay, before what we have studied is there's no change in altitude, but now there's a change in altitude. So now same, the pitot head is blocked, but the static pressure inside the instrument case and the capsule will be different as the altitude changes. So when the aircraft is climbing, alright, when the aircraft is climbing, the static pressure inside the case will decrease, right? The static pressure inside the capsule will decrease. What was the purpose of the static pressure in the instrument case? Was to cancel out the static pressure in the capsule. But as the value of the static pressure inside the capsule case is decreased, the static pressure cannot fully cancel out the static pressure inside the capsule. And this is the reason the ASI will show higher than actual, which means it will overread. So on the other hand, when the aircraft's descent, what happens is that the static pressure inside the instrument case is increased, but the static pressure inside the capsule is unchanged because the pitot head is blocked, right? So what was the purpose of the static pressure? Was to cancel the static pressure inside the capsule. but the static pressure value is more inside the instrument case compared to the static pressure inside the capsule, and thus it cancels some of the dynamic pressure also, and thus the needle shows lower than actual and thus it underreads. Alright. So in conclusion, it is written that with a blocked pitot source, the ASI overreads in climb and the ASI underreads in descent. So next we will understand the situation 3, which is the static head is blocked. So when the static head is blocked and there is a change in altitude, the static pressure inside the capsule changes, but the static pressure inside the instrument cases remains unchanged, and now it is reversed, that means. And when there is a descent, what happens? In a descent, what happens is the static pressure inside the capsule is increased, but the static pressure in the instrument case remains unchanged, right? So what was the purpose of the static pressure in the instrument case? Was to cancel out the static pressure of the capsule, but it cannot, because the value of static pressure in the instrument case is lower compared to the static pressure in the capsule. So the ASI overreads. The ASI will show more than actual. So let's understand the next, when the aircrafts climb. So when the aircraft climbs, what happens is the static pressure inside the capsule decreases, but comparatively the static pressure in the instrument case remains unchanged, right? So it is more comparatively, and thus the purpose of the static pressure was to cancel out the static pressure in the capsule, but it does cancel out the capsule's static pressure, but some part of the dynamic pressure also, and thus causing the ASI to underread, meaning it shows lower than the actual. So in conclusion, it is written, with a block static source, the ASI overreads in a descent and the ASI underreads in a climb. So there is a mnemonic in the book, which is PUT sort. Pitot block underreads in a descent and static block overreads in descent. So by this mnemonic, you can solve the questions in very less time. So when the pitot is blocked and the aircraft is descending, it's underreads, and when the pitot is blocked, when the aircraft is climbing, it's overreads. When the static is blocked, it overreads in descent, and when static is blocked, it underreads in climb. So it is a very shortcut for you to solve the questions in very less time. Alright. So next we're gonna study about pitot and static leaks. Pitot leaks. A leak in the pitot tube causes the ASI to underread because of the loss of dynamic pressure. So what this is saying is that if there is a leak in the pitot tube, the ASI will underread because of loss of dynamic pressure. Because we know that dynamic pressure is the sole reason of the contraction and expansion of the capsule, which rotates the needle. So if the dynamic pressure is sensed less because of loss of dynamic pressure due to leak, the ASI will underread. This next is when there is a static leak. Static leaks can occur either inside or outside the pressure cabin. A leak in the static tube where the outside pressure is lower than static, which occurs with almost all unpressurized aircraft, will cause the ASI to overread, but probably not significantly with a pressurized cabin. If the leak occurs within the pressure compartment, the cabin altitude will be incorrectly sensed as static pressure, usually rendering the ASI useless. So let me explain you. So there are two situations, when the aircraft is unpressurized and when the aircraft is pressurized. So let me explain you when the aircraft is unpressurized. So what happens is the static pressure inside the instrument casing is comparatively lower compared to the static pressure inside the capsule, cause the purpose of the static pressure in the instrument casing was to cancel out the static pressure in the capsule, but it cannot because the value is way less compared to the capsule, and thus the ASI will overread. Alright, because it cannot cancel out fully, right? Next we're gonna study about when the aircraft is pressurized. So what will happen when the aircraft is pressurized? So if you know that when the aircraft which flies like in 40,000 feet or 35,000 feet, the aircraft is pressurized to 8,000 feet or 10,000 feet, right? So when there is a leak in the static, what happens is the cabin altitude will be incorrectly sensed as static pressure, usually rendering the ASI useless. So it makes the ASI useless. So here's the end of the chapter. You can get these notes on the description, and thank you for watching.